Okay. Then present. Okay. Okay, again, good afternoon. Okay, so today we will start our new chapter. Okay, chapter 3. So our first chapter was on linear algebra equation, and second chapter was nonlinear. And now we are going to I'm going to introduce another new chapter, which is about initial value problem. Okay, initial value problem. Okay. So okay, so there will be of course in numerical this numerical analysis course, there's always several methods. Okay, several methods, several solution options to solve a differential equation, to solve algebraic equation, etc. Okay, to solve the problems. Okay, so today I'm going to introduce to you two methods. I mean two general methods. Okay, to solve initial value problem. Okay, but under these two methods there are other three. Okay, three types. Okay, so okay, there are the three other types of definition for each of the methods. Okay. Okay, but we will see the first one first. Okay, so the first one, numerical solution of ordinary differential equation. So basically, you are going to deal with differential equation. So you have learned about differential equation, I think in Maths 1 and again in Maths 2, maybe. Okay, so we write ODE. Okay, ODE, the short form for ordinary differential equation. So it's actually just normal differential equation, means that it's a derivation, okay? Equation with derivations, first order, second order, or third order, okay? But normally we will use only first and second order. We will apply only first and second order, okay? In our course. Okay, so the differential equation is a set of equation in terms of derivation, differential, okay? So we write it as dy dx or dy dt or y prime. Okay. Okay. So so this is the definition. You must already know about this. Okay. Definition. Okay. So we write it as y prime t. T normally is the times. Okay. Normally. Okay. Normally t is time in second. Okay, so y prime t is written as is a function f in terms of y, depending on y and t. Okay, so means that the y prime is a derivation, differential equation, dy over dx, for example. Okay, so this derivation is a function. Okay, it's a function which is depends on the y, which is the initial equation y. Okay, and times t. Okay, so we write it as y prime t equals to f, the function yt, which is okay. So in initial value problem, we are given with the value of the initial at the starting point. Okay, so normally the starting point is when t is equal to 0 seconds, 0, right? Okay, but it can be, the starting points can be at 2 minutes, 5 minutes, or 10 seconds, 30 seconds, depends. But just that generally, the initial point will be t at 0 seconds. Okay, so we write it as y0, means that y at initial point, okay, at the starting point, and we note it as y0 like this. Okay, the notation, this is just a notation. Okay, y0, when we write y0 like this, it doesn't mean that t is 0 seconds, t is 0. But it means that this is the initial starting point of the differential, the set of differential equation. Okay, the starting point, the initial point, doesn't mean it must be 0 seconds. Okay, depends on the question, depends on the problem. Okay, so we have an example. Okay, we have y prime t. The function, the derivation is 3y plus 5 with the initial point value y0 equals to 1. Okay, normally we are given with this set of equation, means that we know the function, okay, the function of the equation of the derivation y prime, and we know the initial point of y, okay, of y, initial point of y is 1, okay. Okay, ada lagi nak masuk sekejap. Okay, so when we said that y0 equals to 1, is not 3y plus 5 equals to 1, okay? Bukan, so you have to read it carefully, okay? Don't mix it around. So when we say 3y plus 5 is y prime, and we know that y0, the initial point is 1, so it's not like this, okay? Not 3y plus 5 equals to 1, because this is y0, so we have to integrate. So if we integrate this function, it will be 3y square over 3y square over 2 plus 5t, okay? Plus 5t, okay? So no, y, sorry, this is function y. Okay, 3y square, okay, plus 5 plus 5y. So this will be equals to 1. This is between t ni. 3t ni. This is what? This is 3t should be. Okay, 3t. So pelik. Okay, this is just example. I want to show you that we normally we are given with the function of derivation, and then the initial point at y. Okay. Later on, we will see. I will give you another example. Okay. So another set of equation is ty plus 1. Okay, with initial point y0 equals to 0. Okay. So we are normally we are asked to calculate, okay, solution for each time steps. Okay, so we are given the time step. The time steps is called here h. Okay, so for example, the function, okay, is valid. Okay, how do you say? Okay, means that, okay, the function is valid for a period of time of 10 seconds. Okay, t from 0 until 10 seconds. Okay, and then we are given with the step size, time step or step size h. For example, we use h 0.2 seconds. Okay, 0.2 seconds. 0.2 seconds. Okay. Just now, the period of time, the total period of times is 10 seconds, for example. Okay. Yes, and step size is 0.2 seconds. So we must we have to solve, okay, the function y for each time step. So if we have 10 seconds, so we must have 50. 50. 50, okay. 5, sorry, 5. Okay. 50 lah, betul lah. Okay, 50. 50 saja, means y1 until banyak pula. y50. Okay. But this is a lot lah. Normally, if we have to do normally, manually, we just have like 4 or 5 or maximum 6 steps. Okay. Okay. So we're given with this step size. So we have to calculate the solution of y of the function for each time step given. So if we start with 0, so t0 is 0, t1 is 0.2 seconds, for example. T2 is 0.4 seconds, and until we reach the final tf, tn or tf, final. Okay. Okay, so we increase the tn, okay, for each time steps, okay, until we reach the final value. Okay, so this is what I was talking about. So we have two methods to solve the initial value problems. So the first one is Euler method, okay. So in Euler method, there are 3, okay, different types of correlation, we say, okay, equation correlation, okay, that we can use, which is called as forward Euler method, backward and modified, okay. Okay, I'll show you the equation later on. And then we have Range-Kutta methods, okay, which is in second order, third order, and fourth order, okay. The higher the order is, the more accurate the results, okay. The results that we calculated will be more approach to the exact solution, the higher the order. Okay, but of course, the higher the order, the more complicated and the longer time it takes to solve, okay, to calculate. Okay, so this is the forward Euler method, okay. So it is actually derived from the definition of derivation, okay. So look at here. Consider the forward difference approximation for first derivative, okay. So this equation, this is not new, okay. This is not new. This is not something new to you. Okay, this is from the definition of derivation. Okay, if you know definition of derivation, how do we derive an equation? Okay, so a derivation is actually the difference of if you do a graph, okay, the difference of in y axis divide by the difference of the x-axis, okay, which is h, the time steps here, okay, h, okay, and we get the slope, right? If we imagine a graphic, so that is the slope is the derivation, right? So this is from the definition of derivation, first derivative, okay. So h is the time step, which is the difference of the step size, okay. So if you rewrite the definition of the derivative, first derivative, we have this solution, this equation, okay. So we rewrite it, just put the n plus 1, yn plus 1 on the left, okay. So we have this equation that we can say that this yn prime is a function of yn and tn, because yn is a function of tn, okay, and y prime is a function of yn, so that's why, okay, yn and tn. So we can write, okay, this yn, this Euler method, okay, in for each time steps, okay. So y1, starting from y0, normally y0 is given, okay, the initial point is given, that's why we said this is a initial value method. We have the initial value, and then we have to, from this initial value, we have to derive the subsequence, okay, the next what's going to happen, means that we predict, okay. It's like if we apply this method, this initial value problem in any engineering problem, it's like we are trying to predict what's going to happen in 1 hour, okay, for example, in 1 hour or in 10 seconds, what's going to happen to the whatever experiment that you are running, right? So so that's why we calculate, okay, for each 0.2 seconds, then what will happen after 1 minute, what's going to happen, etc., until the final period of time, okay. That is the definition. If you try to imagine what is this Euler method for, okay. Euler method for is like we are doing a prediction, okay, prediction to the experiment or any analysis that we're going to run, right? We're going to predict what's going to happen. So why, from the starting point, we know the starting point, and then what's going to happen when the experiment is finished, okay. So we can write from this yn plus 1, we can write all the differential equation, y1, y2 until yn, depends on the total period of time and depends on the step size, okay. Okay, I think it's clear. This is you just apply for example, n0. So you put n0, and then yn plus 1 is y1, and then you proceed y2, yn until yn. Okay. Okay, so this is example. Solve y prime ty plus 1. We have the initial point is given, which is y0 is equal to 1. Okay, so t is 0 until 1. Okay, means normally it is in seconds. We use the SI unit, so 0 until 1 seconds. So you have the step size is given, h 0.25 seconds. So means that we have to calculate the final point will be y4. Y4, right? Because y0 is t0, y1 is 0.25, y2 is 0.5, and then y3 is 0.75, and y4 the final will be 1 seconds. So if we have this type of problem, we are given with this type of problem, means that we have to calculate until y4 because the total period of time is 1 seconds and the step size is 0.25. Okay. This is the example of calculation. So T00, we have Y01, which is given, and then T1 0.25. So we apply the Euler method. Y0 equals to Y1 equals to Y0 plus H, the step size, okay, times Y0 prime. So that's why we have to calculate the previous, okay, the first initial point first. Okay, and then we proceed with the higher point. Okay, so calculate here. So we get 1.25, and then with T2 0.5 we get 1.5781. Okay, just calculation. Okay, I didn't show you. I don't show you the until y4, but just to show you the graph of the solution. If we calculate until y4. Okay, the 4 step size, okay, the final point, 1 seconds until the final point, 1 seconds. So we will have kind of like this, the solution by using the forward Euler solution. Okay, so it is approaching the exact solution. Okay, so okay, like this. Okay, there is the forward, which is the most for Euler solution. The most used is the forward, okay, because it derives directly from the first derivative equation. Next is the backward. Okay, actually it's nothing different, not really different from first backward. Forward, this is backward. Okay, so first derivative, okay, of the backward Euler method. So actually it's the same, just that we start with yn, and yn we use yn plus minus 1 instead of just now we have yn plus 1 and yn, right? Okay, so if you imagine in graphic, okay, forward method, we apply the first derivative at forward point, okay, future point. With the backward method, we use the previous point. Okay, it's just that. Okay, but otherwise the equation is the same from the first derivative equation. So we have yn equals to yn minus 1 plus h yn prime. Okay, so from here we derive the set of equation for all y1, y0 until yn. Okay. Okay, so backward, the same problem as just now. Okay, but here this time we use the backward method. So by using backward method, we have this equation. We have to divide, and we get 1.33 at T1. Just now T1 1.25. Okay, it's just different. The difference is not too big. Okay, 1.25, and this one by using the backward we have 1.33. Okay, so T2 until T4. Okay, so this is the calculation. Okay, next is the, okay, so this is the graph. Okay, imagine, okay, so if we use the backward Euler solution, normally we will the solution that we achieve is higher, a bit higher than the exact solution. Just now by using the forward, we have a lower lower predicted solution, right? By using the backward, we have higher solution that we predicted. Okay. Okay. The third one is the modified Euler method. Okay. So this modified method it is by applying the trapezoidal rule, trapezoid. Okay. Okay, so we use the different here is that, okay, we use both yn plus 1 prime and yn prime in the equation. So means that it is a bit slightly complicated, not complicated, but slightly a longer, okay, time to calculate, because we have to calculate two derivations. Okay, yn plus 1 prime and yn prime, and then we divide, because we have two here, two differential equation. Sorry, so we have to divide the time step by 2. Okay, that is why it is said to be, it's like a trapeze. Okay, trapezoidal rule. Okay, okay, but this is just definition. So again, with the same example, ty plus 1. So by using the modified method, okay, okay, so this is the equation, the general equation. And then, okay, said that with modified method, we are approaching the exact solution better. Okay, of course, because it is more scrutinized, more delicate. Okay, more precise. Okay, so by using the modified Euler method, we are approaching the exact solution as much as possible. Okay. Okay. Okay, everyone. We will do example after I finish all the slides. Okay, we will do one example by using Euler method and Runge-Kutta also. Okay, at least we try to calculate one example, so that you will be familiarized with the equation, okay, the steps given. Okay. Okay, next. Okay. Runge-Kutta method. Okay, Runge-Kutta method. Okay, this is Runge-Kutta method. I think you already heard about this in Maths 1. Oh, Maths 2. Okay, Runge-Kutta method. So, okay, so we start with second order. Okay, second order, Runge-Kutta method. So, okay, so Runge-Kutta method. Again, it's like we apply the trapezoidal rule. Okay, but this time we integrate the function. Okay, the derivation. Okay. So we have yn plus 1 equals to yn and the derivation of the function y. Okay. And then, ada lagi nak masuk. Okay. So we estimate the yn plus 1 by the in the end, this one, we apply the Euler method in this one. Okay. Ada lagi tak? Okay, I think this is explained better. Okay. Or in a more standard form as, okay, so we apply this form. Okay, it's easy. Okay, this form. Okay, just now it's just a definition. Okay, so we use this form. Okay, yn plus 1. So for second order Runge-Kutta method, we use this one. Yn plus 1 equals to yn plus 1 over 2 k1 and k2. And what is k1, k2? K1, k2 is k1 h times the function yn, or the derivation. This is the derivation. And then k2 hf yn plus k1 tn plus 1. So you have to calculate k1 and k2 first, and then substitute in the equation, and we get the yn plus 1. So starting from the y0, and then we have y0 y1, and then y1 used to get y2, etc. until yn. Okay, this is second order Runge-Kutta method. So of course the third order will be longer. Okay, so third order. Okay, so this is the third order Runge-Kutta method. So we have yn plus 1 equals to yn plus 1 over 6 k1 plus 4 k2 plus k3. Okay, so the equation is already being simplified. So the actual equation is like this with the integral, etc. Okay, so this is the simplified form. Okay, so it's written as in K1, K2, and K3, this parameter. So we have to calculate K1, and then K2, and then K3. Okay, and then we get the Y1. Okay, and that is just for Y1, and then we have to repeat for Y2, Y3 until how many times steps, okay, that we need to calculate. So it is longer, but it is more accurate by using this Runge-Kutta method. Okay, and then the final one is the fourth order Runge-Kutta method. Okay, so the fourth order, so fourth order yn or yi here, plus 1 over 6 k1 plus 2 k2 plus 2 k3 plus k4 and times with h. Okay, this time the h is included behind. Okay, and then so k1, k2, k3, k4. Okay, that is just the definition. So you don't have to remember the equation, this equation, okay, since it is open book. So you don't have to remember this, just that you know how to apply. Okay, so that's why we have to do at least one example together. Okay, so that you know how to use, okay, this equation. Okay, so actually that's all for my slide. So now we have to do example. Okay, okay, I'll give you this equation. First, we will try to solve this differential equation by analytically. Analytically means that using manually, your knowledge of how to solve a differential equation. So you have this one, dy dt, dt equals to yt square minus 1.1 y. Okay? dy dt, the differential equation, equals to yt square minus 1.1 y. Okay? So first, I want you to try to solve this equation analytically. Analytically means whatever you know, the knowledge that you have learned in order to solve differential equation. Okay, this is just first order, right? Okay, so it must be simple for you. So how do we solve this without learning, without learning today's lesson? You know how to solve this, right? You know how to solve this equation. So how do we solve this equation? Okay, this differential equation, how to solve it? We have to integrate it. Okay, we have to integrate. But before we integrate, before we do the integral, normally, okay, the approach that we use is that we try to rearrange the left hand side and the right hand side. We try to rearrange it according to the what we call this y, t, the different term. Okay, so we will arrange it so that the y, all y's will be on the left, okay, dy over y. Okay, we will try to arrange it, and this one, t square minus 1.1 and dt, okay, over there. So we have dt. Discipline. Okay. Okay, we rearrange the equation so that we have all the y's term on the right hand side and t's on the left hand side, or whatever, left hand, right hand. Okay. Okay, we arrange it that way so that it's easier for us to integrate. Okay, so we have dt here and dy here. So we integrate. We do the integral. Okay, so dy over y will be ln y, ln y, ln y. And t square minus 1.1. Okay, integrate. So t power of 3 over 3 minus 1.13, yeah. Okay, so okay. ln y equals to t cube, t power of 3 over 3 minus 1.1 t plus, don't forget, plus constant. Plus a constant, okay? Okay, so we do a normal integral. Okay, normal integral. Okay, but we have not finished yet. We have to, since we know this is the about initial value problem. Okay, initial value problem, and we know, okay, the initial value is given, I forgot. Okay, y0 equals to 1. Y0 equals to 1, huh? Oh, okay, y0 equals to 1 and t is from 0 until 2. Okay, 0 until 2 seconds. Okay, this is for later on. For Euler and Roche-Coulthard method, we have to apply this. Y0 equals to 1 and t from 0 until 2 seconds. Okay. So now we have a constant that we have to solve. We have to search for this constant. Okay, so by knowing the initial point, so we substitute the initial point in the answers that we already the integration equation that we already have here. Okay, saya kena padam.
Doctor.
Yes.
For the left side, we will keep the ln y, or will we do the exponent e to the power ln y so that the right side becomes e to the power t cube? I mean, doctor, in the left side, will we keep the ln y or make it only y in the left side of the equation, doctor?
Left side,
will we keep it like this, doctor, ln y, or will we make it y equals to
okay. We will make it y equals to something exponential, right? Okay.
Yes, doctor. Should we do that, or can we keep it like this way, doctor? Because it is actually simplified. If we do the exponent, it will become complex, doctor, right?
That's sure. Okay. Normally, I will change it into exponential so that I have just y equals to something.
Okay, doctor.
Okay. Okay. Yeah. So we have y, okay, exponential. Okay, t power of 3 over 3 minus 1.1 t plus constant. Okay. So so we know that y0 is 1. So mean that if t is 0, so this is 0, 0, constant. Okay, so we have okay, y0, okay, equals to c, which is equals to 1. Okay, because this is all 0, so e exponential 0 is 1. And so we are left with c, or the constant. Okay, so constant is equal to 1. Okay, because y0 equals to 1. So our answer will be y equals to exponential t just now, t power of 3 minus 1.1 t. That's it. Okay, because c is 1. This is c, constant is 1, so no need to write it. Okay, so this is by analytically solve the equation. We have y equals to exponential t power of 3 over 3 minus 1.1 t. Okay? Okay, everyone?
Okay, doctor.
Okay. Tidur lagi ke yang lain?
Okay, doctor.
Yeah. Okay, now we are going to apply the Euler method. Okay. Okay, we use the forward method je lah. Okay, the forward one. Okay.
Hello doktor.
Yeah.
Yang tadi tu doktor pakai cara biasa kan?
Yang tadi tu, yang first tu, tu cara biasa, just nak revision balik tentang yang korang dah belajar lah
kita belajar
sebelum ni.
math kan? Yang tadi tu.
Yes, cara selalu belajar maths. Okay?
Okay.
Okay, now kita nak apply yang method hari ni, okay? Okay. 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 So forward method, okay, this is the forward method just now, yn plus 1 equals to yn plus hyn prime. Okay. Let's see. Okay. Okay, in the question is given 0.5 and 0.25 times step. There are 2 times step, but we will do only 1 time steps, otherwise it will be too long. So I will use this one here, h 0.5. Step size h 0.5. Okay. So means how many time steps, how many y's time step do we need to calculate until we reach the final value? Because we have t just now 0 until 2 seconds and the time step is 0.5. So it means that we have to calculate until t0, y0, t1 is 0.5, y1, t2 T2 is 1 seconds, Y2, T3, Y3, T3 is 1.5 seconds, and T4 is 2 seconds. Okay, faham tak? Okay, when we write T1, T2, okay, like this, and T0 of course, so this is 0, 0.5, 1, 1.5, 2. Okay, because the time steps given is 0.5. So we will need to calculate y0 is given, y1, y2, y3, until y4. Okay, whatever the method, we have to calculate until y4, the final. If the question give you 0.25 time step, so we need to have total until 8 points, y8. Okay. 0, 0.25, 0.5, 0.75, 1 until 8 you have 8 time steps, okay? But now we use only this one, 0.5. Okay. But of course the smaller step size, the smaller the h this step size, the more accurate the results will be. Okay? Means that we are more precise. Okay, but here we are doing this manually, so we use only this one. Okay. Okay, so what do we need to do first? Okay, this equation. So y0 is 1. So we know y0. So in order to calculate y1, what do we have to do? Y1. Okay, we need to solve this function prime. Yeah. Okay. So start with y1. Sorry. Okay. Y1. Okay, sorry, pernah lost. Okay. Yn prime dulu. Okay, sorry. we write yn prime. Okay, the equation just now is yn tn square minus y.1, the general equation just now. Okay, so we write yn prime is yn tn square minus 1.1. Okay, so this yn prime. Okay, so y0 t0 y0. Okay, so y0 prime y0 t0 square 1.1 like this. So y0 is 1. This is 0. 1.1. So this one will be negative 1.1. Okay. Okay. 1.1, negative 1.1. Okay. Okay, so we have this one. Okay. And then to calculate y1, so y1, y0 which is 1 plus the step size 0.5. So in bracket y just now minus 1.19. Okay, so this is the answer for y1, which is, if you calculate this, 0.45. 0.45. Okay, so this is your this is our y1. Okay, so we have repeat back. Okay, so we have to calculate yn prime first, because we know y0 is given, so we have to calculate y0 prime, and with this y0 prime we will get the y1, and then next step, y1 prime, okay, and plus multiply h and plus y1, we will get y2. So y2 will be y1 plus h and y1 prime. Okay, y1 prime, if you calculate, will be the negative 0.3825, and y1 prime, so y2 will be 0.26. Okay. Okay, try to do this slowly, okay, before I give the all the answers. Okay, try to do this. Okay, I want you to apply the equation by yourself so that you understand better. Okay. So proceed until T4, which is Y4 at 2 seconds by using the forward Euler method. Okay, saya bagi masa sikit untuk calculate. is better in your exam or anything. Okay, it's better when you have calculated all the answers. You write it in a table. Okay, so you just put from T0 until T2 seconds, from Y1, Y0 until Y4. So what is the answer? Okay, and Y1 prime until Y4 prime. What is your answer? So you tabulate all your answers in a table. Okay, so it's clearer, much clearer. De- dekat RNR. Doktor nak tanya, for this syllabus Euler Erosh kata method ni more on progression kan, bukan iterations kan, sebab sebelum ni punya method pakai iteration. Ya, so Euler Erosh kata ni progression kan sebab dia pakai iteration. Yes Hanif. Macam tadi saya cakap, tak tahu dah masuk ke belum. Macam initial value problem ni kita guna macam kita nak predict kan. Kita buat eksperimen ke apa ke. Kita nak predict what's going to happen after 10 seconds, after 1 hour ke kan. So we have equation ataupun correlation yang prinsipal yang kita dah ada. So kita macam apply that correlation or that equation and to predict lah apa yang akan berlaku after habis eksperimen tu, apa yang akan berlaku pada kita punya tu lah. Macam tu lah kita predict in the 10 seconds, 1 minute or 1 hour. So and we see whether our prediction tu is approach to the exact solution ke tak kan after that. Ya, dia lain sikit. Yang sebelum ni kita buat iteration. Ni dia punya, ni adalah nak solve problem lah. Okay ke everyone? Better cuba better you guys try to apply the equation, try to calculate so that nanti bila nak exam nanti baru nak terkial-kial nak apply tu, nanti tak tahu macam mana nak apply. Even though you don't need to hafal to memorize all the equation, but you know how to apply it, so you will save time. Apa dia cakap? Okay. Ada yang on the way balik campus ada yang kat rumah ni. 0.45, 0.26. Okay.
Doktor,
Ya.
kita cari sampai Y4, Y5.
Yes. Y4. Sebab bila kat Y4, T will be equals to 2 seconds kan? Which is dah habis lah eksperimen tu, macam tu. Dan kita set tadi, T sampai 2 seconds. So dia depends. So tadi saya tunjuk contoh, kalau step size dia kita set 0.25, so dia sampai Y8 lah, lagi banyak lah. Dia lagi kecil macam tu. Sometimes step size tu is not given. It depends on us wisely. How are we going to nak letak to put the step size to how much. Okay, just now let's see buat table. Okay, I'll give the answer in table. So in your final exam ke or whatever lah, homework apa ke, you do the same table. Okay, so we have T, Y and Y prime lah. So we have 0, 1, okay. Another column actually 3 or 4. Okay, so y. So this is 0, 0.2, 0.5 I think first. 0.5. 0.5, 1 seconds, 1.5 and 2 seconds, okay? So y0 just now is 1, y0 prime, apa tadi? Mana tadi? Y0 prime. Y0 prime, negative 1.1. Negative 1.1. So y1 0.45, 0.45, y1 prime negative 0.3825, t2 at 1 second, y2 is 0.26, y2 prime negative 0.026, T3 1.5, 0.247, 0.247, Y3 prime 0.284, 0.284, and T4 2 seconds, 0.689, and Y4 prime. Jadi Y4 prime is not needed anymore. Tak apalah, kita nak lengkapkan table ni. Just want to complete the table. Actually we already achieve Y4 here. Okay, 0.689. Okay. I'm not sure using the analytic result just now, if we put t equals to 2 seconds in the exponential answer just now, how much y do we get? I didn't compare. Okay. Sekarang saya tak ada exponential. If you guys want to compare, you can compare the answer. Okay, y4 or when t equals to 2 seconds, from the analytical result just now using the exponential, the integral, how much y do we get? Okay, and this one we have 0.689. Okay. Ketiga dah cukup ya. Okay. Okay, so this is with step size 0.5. Okay, you can do as your homework by your own self. Saya tak sema, but just for your own good. Try to do the calculation the same with the same problem, but with step size 0.25. H equals to 0.25. So you will get you will have y1, y0 until y8. Okay, you can try that by yourself. Okay, just to see the difference and just to familiarize with the equation forward method. Okay.
Doktor nak tanya.
Yeah.
Kalau saya dapat Y3 tu 0.246 dengan Y3 prime 0.283, jawapan untuk Y4 memang dia akan lari ke sana?
Of course tak apalah. Tak apalah, tak ada tempat tu dah okey lah tu. 0.03 3 decimals precision tu.
Lepas tu Y4 saya 0.387.
Oh, lari banyak. Saya yang silap calculate. Tak tahu. Tapi tak apa, you can verify the calculation. Kalau betul saya silap lah, tak apalah. Apa tu, otherwise kalau different sikit tu tak apa, tak ada masalah. So, faham je kalau dia start kat awal tu slightly different and then dia akan drag lah kan. But okay lah, saya terima je jawapan kalau lari sikit-sikit tu.
Okay, Doctor. Thank you.
Okay. Okay, so this is the Euler, forward Euler method. So try to solve this with step size h 0.25 ya, 0.25 seconds. Okay, next we are going to use the Runge-Kutta method. Okay, Runge-Kutta method, fourth order terus fourth order. Kita buat fourth order terus sekali. Okay, because if you do the second and third order, if you do the fourth order, we still have to apply the second and third K1, K2, K3. Okay. Okay. Runge-Kutta method. Wait lah. I want to switch on the light. Okay, Runge-Kutta method. Okay, dang, is it open? Okay, we use this one. Okay, so y, okay, I don't need to write it back here. So yi plus 1 or yn plus 1 equals to yn plus 1 over 6 k1, 2k2, 2k3 plus k4 h time steps, okay? So by using the same time steps 0.5, h is 0.5, we try to apply this Runge-Kutta method, okay? So we will start with by calculating the K1. Okay, K1 So K1 is actually the derivation, the y prime. Okay, K1 is actually Tn yn, which is actually the y prime just now, yn prime. Okay, but we start with 0. So K1, the first K1 will be y0 prime. Y0 prime is now is negative 1.1. So saya tak payah calculate I don't need to calculate again. So this is y0, y0, 0, 0, 0. So K1 is y0 prime, which is just now we have calculated, minus 1.1. Okay, K2 for the first time step, okay, means that we are trying to calculate first one, y1. So in order to calculate y1, we need to calculate all the k1, k2, k3, k4 for y0 first, and then for y2, repeat it again. So it is longer than Euler method. K2 is okay, Tn plus 1 over 2 h, Yn plus 1 over 2 K1 h. Faham tak? Okay. That's why we need to try to apply this. Otherwise, we will not be familiarized with this equation. So what does it mean here? How to explain to guys? Okay. Okay, so try to look at T0 first, alright? T0 plus 1 over 2h. Okay, 1 over 2h. Okay. 1 over 2h, comma, okay. Yn plus 1 over 2 k1h. Okay, y0 plus 1 over 2 k1 h. Okay, so if we write, if we substitute the value, so T0 is 0, okay, 1 over 2 h. H is 0.5, so 1 over 2 is 0.25. So 0.25 plus 0, 0.25. Okay, this part, the first term, 0.25, okay? and then comma, okay, y0. Y0 just now, y0 is 1. Okay, y0 is 1. Plus 1 over 2 k1. K1 is minus 1.1. So you need to calculate somewhere. Okay, like this. 1 y0 plus 1 over 2 k1 negative 1.1 multiply with h 0.5. So you need to calculate this. Okay? To get this value. So this is 0.45. 0.45, huh? This one, 0.45. Okay? 0.45. Okay, now, how do we solve this? What does this equation means? This function means 0.25, 0.45. Okay, again, this function f is actually the derivative of the y. So it is actually y prime. So look back at our y prime. What is y prime? Y prime is dy dx, dy dt. Okay, so y prime just now. Y prime. Okay. So y sekejap y ini. Okay. Okay. Y prime. Okay. Okay, so our differential equation just now we have y prime. So here is y0 prime. Okay, for the first step, y0 prime is y0 just now. Y0 t square minus 1.1 kan? Okay. The equation, the general equation at the beginning. Okay. So for this function, 0.25 is the t. Okay. Y0, y is the 0.45. So it's better we don't write y0. Okay, 0.45. Because y here, this is our y, this will be our t. Okay, so y is 0.45, t is 0.25, square minus 1.1. Okay, so we have negative 0.467. Okay, so okay, we cannot write y0 prime. This is k2 actually. K2, okay? So letak biru Okay, this is k2, okay? So we have k2. Okay, the definition of k2 is function of t0 plus 1 over 2h, y0 plus 1 over 2 k1h. So after we calculate those terms inside here, we have the function of 0.25 t untuk t, for t, and for y is 0.45. Okay, so this function is actually the derivation, the derivation function at the beginning. So this, that was y, which is y t square minus 1.1. So the y here now is 0.45. T, our t is 0.25 square plus minus 1.1. So we have minus 0.467. That is for K2. Okay? Okay. So panjang Sekejap. Baru Y1 tak habis lagi. Okay. This is K2, okay? 0.467 Okay, sebab dah balik. Now we calculate K3. K3 Okay. I erase this, okay? Okay, this klik kat atas. Jadi negative 0.467. Okay, K2. Now K3. K3. So K3, the function Tn or T0 here for our first step. T0 plus 1 over 2h, so the same. So we have function 0.25 again for T. And for y, it will be yn or y0 here plus 1 over 2 k2. So it depends on your answer k2 just now. K2h. Okay. So if we substitute in there, we have 0.883 for y. Okay, which is will be negative 0.916. Okay, after we get this function equation, so we put this value inside the derivation y in the beginning equation, from the beginning equation. So we have negative K3 negative 0.916. And K4, finally, K4 is function of T0 plus H. So T0 plus H is 0.5, okay, because T0 is 0. So we have F 0.5. And then yi plus K3H will be 0.542. Okay, nanti 0.542. This is the y0 plus k3h. Okay, so we get k4 negative 0.461. K4. Okay.
Okay, doctor.
Okay. I know it takes time for guys to calculate, but I'll give the answer first, okay? Okay, so this is our K1, K2, K3, K4, but we have not finished yet. We have to, so once we achieve all these K1 until K4, then we can calculate only Y1. Okay, not yet Y4. Y4 is a long journey. Okay, Y1 first, okay? Y1, so back to the general equation, okay, Y1, so this one, the fourth order Rajkuta method, so Y1, is Y0, which is 1 plus 1 over 6, K1 plus 2K2 plus 2K3 plus K4 and multiply with H. Okay, so that is Y1. Okay. Y1, you will get 0.64. 0.64. So that's how you got that's how you got Y1 by using fourth order Rajkuta method. Okay, then you have to repeat for Y2 again, K1 F T1 Y1. So now it will be T1 Y1, not T0 Y0 anymore. Okay, and then K2 and then K3 and then K4 and then calculate Y2, and then again K1 P2 to get the next step. So you have to repeat that until Y4. Okay, because we have chosen to do the time step H 0.5. Okay, so we have until Y4. So by using this Rajkuta method, the process is taken more time. Okay, because we need to calculate K1 until K4, and then we arrive at Y1, and then K1 till K4, and then Y2, K1 till K4, Y3. until the final. Okay. So saya sampai sini je. I only have these answers. Okay. The rest you have to calculate by your own self. Okay. Just need to practice. I think this is not hard. It's just that we have to practice and we have to memorize what value to put inside the equation. Okay, this function. Okay. Okay. Otherwise, I have finished the example. Okay, just that you guys need to finish the calculation. Okay, do you have any questions?
Doctor, there's second order Rangi-Kutta method, third order, and fourth order. We can apply any of it in any differential equation, Doctor.
Yes, we can apply in we can apply any of them. Yes, but if you're asking for your exam or anything, I will ask. Okay, which method to use? I will mention which method to use.
Okay, Doctor. Thank you, Doctor.
Apa lagi? Okay. Any more questions? Our next chapter will be partial differential equation, PDE. You have heard about this before, right? This is ODE, ordinary differential equation, and then you have partial differential equation. So partial differential equation, we have to apply the initial value problem and boundary value problems. Okay. Or you want to? Okay, so I'll give you the attendance form to fill in. There are 50 of you today, plus Amin kot dari terpaksa keluar. Okay, you can fill in the attendance.
Doctor, can I ask one more question?
Yes.
Doctor, if the differential equation is second order or third order or fourth order and so on, is there any advantage in using different kind of method to solve it, or we can just use any of it? If the main equation is different, Doctor, like second order, third order, and more.
Yeah. Okay. Generally, the more complicated one is the more accurate one. Okay, so if you use like this one, the fourth order Rashkata method is more accurate because it's more, you can see from for example the step size. Okay, the smaller the step size, the more precise we are to approach the exact solution, right? Okay. So whatever higher order of differential equation is always the method, okay, that we apply, that we use. Depends on the method, okay. The more higher level the method is, so it is more precise, okay. And of course, it has some disadvantage also. Okay, sometimes this fourth order Rashkata method, if we try to program it, okay, we can program it, but sometimes of course it takes longer, okay, computation times to solve, and sometimes our program hang or stuck, right? So there is advantage and disadvantage, of course. So we have to choose the wisely, the step size, the initial values. Okay, when we program this method in programming, MATLAB, etc. Sometimes we are not given the initial value problem, or we are not given the step size, so we have to choose it wisely. So depends on our
Experience, doctor.
experience and assumption of the initial values or the step size, etc. So depending on that, we have to play around with that in order to not crash our program, or to not get our program stuck or stop or anyway. Okay.
So, doctor, if I, in the future, hopefully, in the future, in master's or PhD, if I want to get more precise answer to a very complex equation, I should go for the fourth order Rangekutta, doctor.
Okay. For Rashkuta, normally for postgraduate or whatever, okay, for projects, we use fourth order. Yeah, because fourth order is more, because we can program it. We don't need to calculate manually. So we usually we try to use the more precise one lah. Okay, so we choose a fourth order Rashkuta. We try with fourth order first, and after that we see if we can proceed or not.
Okay, doctor. Thank you, doctor.
Okay. Okay, everyone. Stop me. Okay. Stop recording.